Howdy. And so what have we learned so far? We've learned that valence electrons are the outer shell electrons that dominate the chemical behavior. We've learned that all elements in the column behave alike because they have the same valence electron configuration. We've learned that the number of valence electrons is equal to the column number as long as we neglect the transition metals. We've learned that noble gases are very unreactive, and so noble gas configurations are very stable. We've learned that elements tend to try to gain, lose, or share electrons to get the noble gas configuration. This is referred to as the octet rule because all the noble gases have 8 valence electrons except for helium, which has 2. And so the alkaline metals, if they can lose 1 electron, forming +1 ions, they get noble gas configuration. The alkaline earth metals, if they can lose 2 electrons, they get noble gas configuration, and that's why they form +2 ions. The halogens, if they gain 1 electron, they get noble gas configuration, so they tend to form -1 ions. The chalcogens, oxygen, sulfur, if they gain 2 electrons, they get noble gas configuration, and that's typically why they form -2 ions. Aluminum typically forms a +3 ion to get noble gas configuration. And so we learned how the common ions are related to electron configurations and elements trying to get noble gas configurations. We also have learned that the periodic trends, that as you go up and to the right in the periodic table, the strength of the electrostatic attraction between the outer electrons and the nucleus increases. And that's a result of 2 contributions. One, as you go from left to right, the number of protons in the nucleus increases, strengthening the attraction. And as you go down the periodic table, the outer electrons are going into bigger shells, weakening the interaction. And so again, as you go up and to the right in the periodic table, the electrostatic attraction between outer electrons and nucleus increases. And so the size of the atoms actually decrease, ionization energy increases, electron affinity increases, electronegativity increases. You should remember that the ionization energy is the energy required to remove an electron from an atom or ion in gas phase. Electron affinity is defined as the energy released when an atom or ion in the gas phase gains an electron, and electronegativity is a measure of the ability of an atom to draw electrons to itself in a molecule. And so if we think about the periodic trends, they're consistent with how we separate out the elements in terms of metals and nonmetals. And so in the red, you have the metals. They tend to react by losing electrons. They have lower ionization energies. The blue are the nonmetals. They tend to react by gaining electrons. They have more positive electron affinities. And so typically, a metal plus a nonmetal will result in an ionic compound because there'll be a transfer of electrons from the metal to the nonmetal. And so this video is on ionic solids. And it's important because ionic solids are some of the most common compounds that we interact with. Table salt is just ionic solid, it's sodium chloride. A metal plus a nonmetal forming ionic solid. Ionic solids are important in geology. For example, calcium carbonate is commonly found in rocks around the world. Ionic solids are important in biology. For example, modified form of hydroxyapatite composes large portions of bones and teeth material. And so ionic solids are very common and they're very important. After watching this video, you should be able to write down the formula of an ionic solid given its name. You should be able to describe why ionic solids are relatively stable. You should be able to describe what the last enthalpy is, and that the larger last enthalpy, the higher the melting point. You should be able to describe that the last enthalpy is due to electrostatic attraction between the ions. And given a series of ionic solids, you should be able to put them in order of increasing melting point and in order of increasing lattice enthalpy. And so metals tend to form cations. They tend to lose electrons, forming positive ions. To name cations, you just add ion to the name. And so the sodium ion is just the sodium ion. Potassium, when it forms ion, is potassium ion, magnesium ion, etc. Now for transition metals, they can form different charged ions. So for instance, iron can form a +2 ion or a +3 ion. And so with transition metals, typically you need to put parentheses with a Roman numeral corresponding to the charge to it. And so for iron +2, you'd write it iron 2 ion. Iron +3 would be iron 3 ion, copper 1 and copper 2. Now negative ions are a little bit different. Negative ions are anions. We change the suffix to an IDE. And so oxygen goes from oxygen to oxide ion. When sulfur gains electrons, it forms the sulfide ion. When fluorine gains an electron, it forms the fluoride ion. And when chlorine gains an electron, it forms the chloride ion. So again, for metals, when they form ions, you just add ion to the end. For nonmetals, you have to change the suffix to IDE. Now, ionic compounds are just named after the ions that compose them. And so the positive ion always goes first and is also written first in the formula. And so here we have sodium chloride, calcium chloride, and magnesium sulfide. Now notice that we do not indicate that there's 2 chlorines for calcium chloride. You are expected to know that. Calcium is a +2, chloride's a -1 ion, and so you're expected to know, well, okay, I need 2 chlorides for each calcium, and so we do not write that in the name. It's just calcium chloride, and you're expected to know that that would be CaCl2. Now you could also be asked what's the names of the following, and you have to remember that, okay, iron's a transition metal, and so because the chloride ion is a -1, if I have 2 chloride ions, that means that iron must be a +2, and so that would be iron 2 chloride. For here, the chloride, again, is -1, you have 3, so that must be iron 3 chloride. And so for transition metals, again, we include the charge using Roman numerals in parentheses after the name. Now, it's also very important that you realize that the total charge of a compound has to be 0. And so it is composed of ions that do have charges, but the sum of the charges have to be 0. And so for iron 2 chloride, we have 2 chloride ions, which gives you a -2, and then 1 iron 2 plus, and so those charges cancel. The total charge is 0, but the ionic solid is actually composed of charged particles. Again, for iron 3 chloride, you have 3 chloride ions, which is a -3, and then the iron 3 plus cancels, and so the total charge is 0, but it is composed of charged species. And so ionic compounds are formed from a metal plus a nonmetal, or from polyatomic ions. And so calcium chloride, metal nonmetal, sodium oxide, metal nonmetal, iron oxide, metal nonmetal. Now the polyatomic ions, you have to be able to recognize them, and they're very common, and you'll see them throughout your chemistry career. And so I'm going to ask you to memorize a list of polyatomic ions. And so for ammonium chloride, you just treat the NH4 plus as a ion, and so it's ammonium chloride. And then we have the OH, and so that's hydroxide, so we have sodium hydroxide, potassium permanganate, ammonium sulfate. And so again, for these polyatomic ions, they stay together as a group, you treat them as a group, and you name them as a group. But again, you'll see them as long as you're doing chemistry, and so you need to memorize your list of polyatomic ions. Now, it's not that hard as long as you remember how they're named. And so if you look on the top left, you have 4 bromine containing polyatomic ions, and notice that it goes hypobromite, bromite, bromate, perbromate. Now if you look below that, you see the chlorine containing compounds, polyatomic ions, and so that's hypochlorite, chlorite, chlorate, perchlorate. And so when you have 4 atomic ions, polyatomic ions based on the same center atom, it goes hypoite, ite, perate. Now if you look on the right, we have nitrite and nitrate. There's just 2 polyatomic ions in that series, phosphite, phosphate, sulfite, sulfate. And so it's all based on the relative number of oxygens. The fewest number of oxygens when you have 4 is hypoite. The fewest number of oxygen when you have 2 polyatomic ions is just ite. It's also kind of interesting. Notice that the number of oxygen does not change the charge. And so hypobromite is a -1 charge, bromite -1 charge, bromate -1 charge, and perbromate -1 charge. Now if you add hydrogen to it, then it becomes, you just put hydrogen in front, and so you have hydrogen carbonate, hydrogen phosphate, hydrogen sulfate, hydrogen sulfite. And if you have 2 hydrogens, then that's just dihydrogen phosphate. But you should not forget the charges when we talk about acids. The charge is going to be related to the number of hydrogens. And so, for instance, the nitrite ion has a -1 charge, and so that corresponds with nitrous acid having 1 hydrogen. The sulfate ion has a -2, and so sulfuric acid, H2SO4, has 2 hydrogens. But it's not that hard to remember the formulas and the names as long as you remember the rules hypoite, ite, and perate, and that adding oxygen does not change the charge. But again, the polyatomic ions are important because they stay together as a group. And as long as you're doing chemistry, you will see these polyatomic ions. It's like when ammonium chloride dissolves, you get ammonium ion and chloride ion. When magnesium nitrate dissolves, you get magnesium ions and nitrate ions. And when iron phosphate dissolves, you get iron ions and phosphate ions. Now, another question you could be asked is, what is the chemical formula for the ionic compound that forms from potassium and bromine? And so you have to think about, okay, what kind of ion does potassium form? What kind of ion does bromine form? Potassium is an alkali metal, it forms a +1. Bromine is a halogen, it forms a -1. And so they'll form a compound with a ratio of 1:1, KBr. Now, I started with elements in their standard state, which is potassium solid and Br2 liquid. Bromine at center state is a diatomic liquid. And so I balanced the reaction, and so that made me, I had to form a 2 in front of the potassium and a 2 in front of the KBr. Remember, for a balanced chemical reaction, you have to have the same number and type of atoms on either side. And for the final formula, you'll see that for every potassium ion, you need 1 bromide ion. And so again, for ionic solid, it's composed of charged species, but the net charge is 0. And so it's really kind of a cool reaction. What's happening is each potassium atom is losing 1 electron, forming potassium plus ion. Each bromine atom is gaining 1 electron, and then you're forming the ionic compound KBr. You could also be asked, what is the chemical formula of the ionic compound that forms from aluminum and bromine? And so again, aluminum typically forms a +3, bromine forms a -1. And so for each aluminum, you need 3 bromine. And so AlBr3 means for each aluminum, you need 3 bromine. Now again, I started with elements in their standard state, aluminum metal and bromine liquid. And so to cause everything to balance, I have to add a 2 in front of the aluminum, 3 in front of the bromine, and then 2 in front of the aluminum bromide. But for ionic compounds, they're formed of charged species, but the net charge has to be 0.
Pieces of aluminum are cut from a strip of foil. Liquid bromine is placed on a watch glass and the pieces of aluminum are added. As the bromine evaporates, brown fumes are given off. At first, there is no reaction because of the protective oxide coating on the aluminum. An exothermic reaction between bromine and aluminum causes more brown fumes of bromine to be given off. White fumes are also given off. When a fan is turned on, we can better observe the residue, which consists of aluminum bromide, excess bromine, and aluminum.
So again, a cool reaction. Each aluminum is actually losing 3
electrons. The brown
electrons.
color is caused by the excess bromine.
And so each aluminum is losing 3 electrons, forming +3 aluminum ions. Each bromine is gaining 1 electron, forming a Br-, and then they're forming the ionic solid. You could also be asked, what is the ionic compound? What is the formula of that compound formed from sodium chloride? And so again, sodium will form a +1 ion, chlorine will form a -1 ion, and so the ratio has to be 1:1. Element center state, chlorine is a diatomic, and so I need 1 sodium for each chlorine. And so again, the ionic solid itself is charge neutral, but it is composed of charged species.
A small piece of sodium metal is placed in a flask containing yellow chlorine gas. The flask also contains sand to prevent the heat which will be generated by the reaction from cracking the glass. Initially, no reaction is observed between the sodium and the chlorine. The reaction will be initiated by adding a drop of water to the sodium.
We can actually look at that reaction again.
When a piece of sodium metal is added to a flask of chlorine gas, a vigorous reaction takes place that releases a lot of energy, and sodium chloride, a common table salt, forms. The chemical details of sodium chloride formation are similar to the formation of many other simple ionic compounds. Let's view the process of ionic compound formation on the atomic scale. Many chemical reactions occur through a series of steps. In the process of ionic compound formation, the key step is electron transfer from the metal to nonmetal to form oppositely charged ions. As a chlorine molecule approaches the sodium surface, yet before it makes contact, electron transfer occurs. Then a series of rapid steps, too complex to detail here, forms free chloride ions that are attracted to sodium ions and energy is released. Let's isolate the key step and examine a simplified version of it. Electron transfer from a metal atom to a non-metal atom. The sodium atom has 11 protons and 12 neutrons in its nucleus, and 11 electrons around the nucleus. The chlorine atom has 17 protons and 18 neutrons in its nucleus, and 17 electrons surround it. The sodium atom transfers an electron to the chlorine atom, and the ions attract each other and release energy. The loss of the electron converts the sodium atom into a smaller, positively charged sodium ion, Na+, while the gain of the electron converts the chlorine atom into a larger, negatively charged chloride ion, Cl-. Let's view this essential step once more. Electron transfer and ion attraction occurs countless other times between the sodium and chlorine. The large quantities of energy released vaporize tiny clusters of ions, and these attract others and release more energy. The clusters eventually aggregate and coat the walls of the flask. And even though table salt is not obtained this way, the product of this reaction consists of the same regular array of ions that makes up any sample of crystalline sodium chloride.
And so we can think about this reaction, the energetics. And so imagine that we're starting with the sodium metal and the chlorine gas. Those are the elements in their standard state. And so you should also remember the higher the energy, the less stable. And so if we want to go from the elements in their standard state, the sodium metal and the chlorine gas, to sodium chloride solid, it's going to take a series of steps. And so we could imagine that maybe we should volatilize the sodium solid. And so we go from sodium solid to the gaseous solid, and that costs about 92 kilojoules per mole. And now we need to break the chlorine-chlorine bond. And so that's going to take 121 kilojoules. And now if we remove an electron from the sodium gas, that's the ionization energy for sodium. It's always positive. And now we have sodium ions and chlorine atoms. Now for this ionic solid, we need chloride ions, as that would correspond to the electron affinity of chlorine, which is 349. Now because we're going from chlorine to the chlorine ions, the 349 is energy released. It actually corresponds to a positive electron affinity. And now we got sodium ions and chloride ions. Also notice that this electron that the sodium lost is actually going to the chlorine. There's just an electron transfer reaction. And so electron affinity is energy released when an atom or ion gains electron. It can be positive or negative. In this case, the electron affinity of chlorine is a positive 349, but energy is being lost by a system. That's why we call it negative. And now if we take the sodium ions and chloride ions in the gas phase and we form the solid, we're going from something less stable to something more stable. Remember when we talked about atomic orbitals, atoms form because the attractive interaction between the electrons and the nucleus. The stronger the attractive interaction, the more stable. Well, it's exactly the same thing here. The ionic solid forms because the stronger the attraction, the lower the energy, the more stable. And so when we take a mole of sodium ions in the gas phase plus a mole of chloride ions in gas phase and form a mole of sodium chloride solid, we actually release 787 kilojoules of heat because the sodium chloride solid is much more stable. Now, the last enthalpy is defined as energy to go from the solid to the gaseous ions. And so last enthalpy is always positive. The last enthalpy for sodium chloride is 787. But in this diagram, we're going from the ions to the solid, and so it's depicted as a negative number. Now, the stronger electrostatic attraction between the ions and the solid, the more stable the solid, and the larger the last enthalpy. And so if we add up all these steps, we see that to go from the sodium and chloride in their standard states to sodium chloride solid releases 429 kilojoules of energy. And so the ionic solid is more stable than the sodium metal and the chlorine gas. And that's why ionic solids form, because they tend to be more stable. Now again, this is not the process how the ionic solid is formed, but it gives us an idea about the energetics, what costs energy and what releases energy. And so what takes the most energy when forming an ionic solid? Well, if we look at it, we see it's the ionization of the metal. Removing an electron from the metal atom took 494 kilojoules of heat. Energetically, why do ionic solids form? Because the lattice enthalpy. When we take the gaseous ions and we form the ionic solid, we're going from no attractive interactions to strong attractive interactions, and so it's very stable. And so if you remember when we talked about ionization energies, electron affinities, why do sodium form sodium plus 1 ions? Well, the sodium plus 1 ion in the gas phase is actually less stable. But when the sodium ion forms ionic solid with the chloride ion, then you get something stable. And so sometimes the process of forming the ion is going to be less stable, but when the ions come together to form the ionic solid, that produces something more stable. And so ionics form energetically because the lattice enthalpy is big enough because the strong ion-ion interaction. Now we can use this diagram like this, or we can also just combine this in terms of chemical steps. These two approaches are consistent. Now, if things are common on both sides of the arrow, they actually cancel. And so we notice that if we add all these steps, we end up with sodium metal plus chlorine gas going to sodium chloride solid. If we add up the energy, we see minus 429 kilojoules. Now we can also write down the energy as products and reactants. And again, it's basically the same thing. And so this would be an exothermic process if that energy is in terms of heat. And so the lattice enthalpy is this measure of the strength of interaction between the ions. It follows Coulomb's law, and so the bigger the charges, the stronger the attraction. The smaller the distance between the ions, also the stronger the attraction. And so the stronger the attraction between the ions, the more stable the solid, the larger the lattice enthalpy, and the higher the melting point. And so it's really cool. Using some simple ideas, we can actually put ionic solids in order of increasing lattice enthalpy, increasing melting point. Now, the most important consideration is this absolute value of the charge of the ions. And so if we look on the table, we see we have magnesium oxide, and so we have a +2 ion and a -2 ion. And again, we're only looking at the absolute value of the charge. And so the magnesium oxide has the largest lattice enthalpy, has the largest melting point. Now, if we look at sodium chloride, potassium chloride, and sodium bromide, they're all composed of +1 and -1 ions. And so they have the smallest ions, and so they have the smallest lattice enthalpy and smallest melting point. Sodium oxide and sodium sulfide are in between because it's a +1 and a -2 ion. Now, if you're asked to put ionic solids in order of increasing melting point or lattice enthalpy, first you separate them based on charge, absolute value of the charge. And then the second thing is you look at size. The smaller, the closer, the stronger. And so sodium ions are smaller than potassium ions, and so that's why the sodium chloride has a larger last enthalpy, higher melting point than potassium chloride. Oxygen is higher in the periodic table, it's smaller than sulfur, and so sodium oxide has a larger last enthalpy, a larger melting point than sodium sulfide. And so the larger the charges on the ions, absolute value, the stronger the attraction between the ions. The smaller the ions, the closer the ions, the stronger the attraction. The stronger attraction between the ions, the larger last enthalpy. Last enthalpy is basically a measure of the attraction between the ions. The larger last enthalpy, the lower the potential energy. The larger last enthalpy, the higher the melting point, the more stable the solid. Now again, the absolute value of the charges is the most important consideration. Now it's kind of cool, the shapes of the crystal ionic solids actually reflect how the ions are arranged and their at the atomic level.
A crystal of potassium bromide has a distinctive shape with perpendicular edges. This shape directly reflects the arrangement of the ions in the crystal lattice. The compound is composed of alternating potassium ions and bromide ions.
Crystals of ionic solids can be cleaved along well-defined planes. Potassium bromide crystals cleave along perpendicular planes. The shape of the crystal, and therefore the angles of the crystal's planes, depend on the submicroscopic arrangements of ions within the crystal lattice.
And so ionic solids tend to be rigid, brittle, have high melting points and boiling points. Those that are soluble in water produce conducting solutions, and these properties all are a result of the ion-ion interaction that forms the ionic solid. And so atoms tend to have noble gas configuration by either transferring electrons or sharing electrons. When a metal element plus a non-element react, they tend to form an ionic compound. If the difference electronegativity of two elements is greater than 2, they tend to form an ionic compound. And so two ways you can tell if an ionic compound is going to be formed: if you have a metal plus a non-metal, or if you have the difference electronegativity is greater than 2. And those two ways are typically consistent, but looking at difference electronegativity is a little bit more accurate. The last enthalpy is a measure of the strength of the ion-ion interaction, is the difference between going from the ionic solid to the gaseous ions. The larger last enthalpy, the stronger the attraction, and the higher the melting point. I hope that was helpful.